Okay, any questions?
Could you explain, please, what is short circuit?
So what is short circuit? What is it? Easy way. Does it satisfy you? No. So what is short circuit? So what don't you like about this explanation?
No, it's good. Could you show the examples?
Why? Because all the current passes through this line, this wire over here. Nothing goes above. Why? That's a good question. Why? Why? Somebody will say that there is no resistance, then I will repeat why. So why does all the current go through the path that has zero resistance? Why? Do they have a conscience that they will try to do something? Okay, so there's a potential difference between this point and this point. Okay. Okay.
Resistance or the other circuit devices we use try to block this movement or slow down.
Try? What do you mean by try?
There is instructions basically are not effectively conducted as a simple wire.
What do you mean by a simple wire?
Simple wire without circuit device.
Without a?
Circuit, like resistor, circuit device, resistor or capacitor.
Okay.
A simple wire is just that. So,
Now if I put a simple wire over here, there will be some current out. Because a simple wire has some resistance, internal resistance. Ideal wire, let's say. But, okay, so again we are back to if you have an ideal wire that has zero resistance, so you are basically saying that all the current will go through that one.
not all.
Well, in the ideal case, all of them.
Because this path is, there is no block, there is no resistor.
So why, I would again say why doesn't it go through the a path that has some resistance, but
Can't we try Kirchhoff law so it's 2 years?
okay, fine. I mean, the solution will give you that all the current passes through this one. I don't think he has any problem with that one. He agrees that all the current will pass through this short, right? But why? What's the physics behind? What's going on in the, let's say, in the microscopic level? So you are the electrons. Just imagine you are an electron just going through around this circuit, and you reach over here. You don't actually know that there's no resistance over here. You are over here. And also imagine that, I mean, when you say that there is no resistance over here, you are saying that the electric field on this wire is also zero. So if the electric field on this wire is zero, why does an electron over here move across this wire? We are lucky that you are not an electron. That's almost a good answer.
Electric paths, resistor change direction.
No, why should it change? I mean, because of the? What do you mean changes direction?
There are bandwidths and electrons moves with the electric path. Electric path doesn't go to the resistor and to the electrons.
Well, there's no electric field over there, here. We are saying that there's no potential difference. If there's no potential difference, then there's no electric field, right? There's no electric field on this line. But still the electrons go along that line, right? We all said that all the current goes through that line. Although there's no electric field.
There will be electrons over there too, but they are not moving, so it's like they are giving that information of there is a potential, high potential over there, but
No, this point and this point, they are the same potential. There is no high or low potential.
it's like they are saying like there is a wall here. There will be, it's like a plane that slows electrons and other electrons.
Because of, for example, this point, yes, this point and left of the, yeah, for example. There is a potential difference between these points.
There is a potential difference between, oh, be careful.
This point and
Okay.
this point.
Okay, so,
Because of this potential.
no, is there a potential difference, sorry? Is there a potential difference between those 2 points?
This point.
Yeah, is there a potential difference? Why? What is it equal to? The current running through the resistance times the resistance, right? The current running through the resistor is 0, so there's no potential difference. There won't be any potential difference. Within our approach, yes.
Why the current does not go up?
It does not. Now that's the question, right? Why does it all go through here? That's what we are discussing.
Electrons don't dissipated energy, maybe. Nothing wants to dissipate energy.
So, I mean, why don't they stay in the battery then?
Because water can't go up. But it's still.
If you use line people analogy, if there's a line people, and you try to move through that line, for example, in a resistor case, this line is very crowded. You are an electron starting from the battery. You try to go, but you push other people.
Okay, so I will ask you, why is this analogy correct?
Because electrons, first is movement of electrons, but they are moving all together, not just one electron jumping through the whole circuit.
Okay.
This is thing called goes to left.
Now, who is going to left?
Electron in cross.
In?
Goes to one
Okay.
way, and it propagates the other electron who wants there.
Well, you see, the Q analogy is bad in the sense that we make choices, right? We choose to go to the crowded queue or the not so crowded queue. We make choices. And you can choose to go to the crowded queue. Electrons are not making choices. That's something bad about that analogy.
try to move.
Try, I mean, whenever you use the word try, just be a bit careful. The electrons do not try.
Electrons are in line.
Okay, so?
And there's a potential difference which is created by the battery.
Well, why doesn't the battery create any potential difference between these 2 points?
Not these 2 points. It's n.
Okay.
One and center. There is no potential difference in this. Before you said 2 points. There is no potential difference.
How do we know?
There is no. There is nothing to create.
Why? I mean, we are just making just circles. I mean, the thing is, so we all agree that all the current will run through this one. If all the current runs through that one, then there is no potential difference across these 2 points. And since there is also zero resistance over there. So these are all the same things. The question is, why does all the current run through this one? Now, the answer is not that the potential difference is zero, because that's basically saying that all the current runs through the resistanceless wire. So let's not shuffle the same observation. Now, the thing is, why?
What I think, there is this battery which basically takes electrons from one side, belongs to the other EMF, which has an EMF. And the electrons are in the left-hand side of the battery. And as the ratio is to lower the potential energy, we're trying to get to the high potential. Right? So, and the high potential is in the other side.
No, hold on. Does everybody agree with him that he said that since the system will try to lower their potential energy, the electrons are going to the higher potential? Do you all agree? Lower potential energy for the electrons means they should go to the higher potential.
So as the electrons are moving, the only way for them to get there, because there must be no potential difference between the two. And
Why?
Sorry?
Why? There shouldn't be any potential.
Because it's in the same conducting wire.
Well, this point and this point is also on the same conducting wire. They are not at the same potential if there is a current running through them.
But there is some kind of resistance.
So why does the resistance make such a huge difference? That is still back. We are back to the original question.
It prevents the electrons from moving through it.
Why?
It's going against the motion.
You see, of course, let's look at it this way. Let's assume that we have a huge door over here, a small one over here, going back to the analogy, and you are all piled up here, and I'm pushing you. Some of you will go through the small door, right? Although there will be more resistance over there, you will go through the small door. Some of you. Not over the huge one, but the electrons do not, almost.
In this example, it's not the ideal case. This example is that one wire has more resistance, one wire has huge resistance. But in this case, one wire has no resistance.
Okay. So what does it mean to have a zero resistance wire?
It means that the potential current that would be there would be infinite.
No, you see, we had a big microscopic picture of the resistance. Do you remember it?
Is it like, it literally doesn't go down? Is it like that, or some of it?
It doesn't go there. If you remember, we had a relation between the resistivity and the drift velocity. Yes.
Electrons bounce back and push other electrons that tries to come here and send it to the other way. That's why it can't go there.
Okay, what's the relation between the resistivity and the drift velocity? Do you agree? So zero resistance means zero resistivity, which basically means infinite drift velocity. which basically, well, of course, infinite in the, we are not doing any relativistic mechanics. We are assuming that everything is actually much smaller than the speed of light. All the changes are much smaller than the speed of light. So, and this is when the drift velocity is infinite, of course, our approach will break down anyway. But let's just assume, for the sake of simplicity, that for a sufficiently large drift velocity, the resistivity will be almost zero.
What happens in the real case, in a real superconductor? If the wire,
In a real superconductor, you cannot attach a battery. If you attach a battery, the battery dies.
which is battery flat,
You cannot create a potential difference across a superconductor.
isn't this similar?
Here, well, we have this resistance over here, this very small one.
Okay, all I was saying was that the short wires is the wire on top.
Well, sorry, for the superconductor, this description already breaks down anyway. The resistivity is just zero, independent of the drift velocity. You cannot say the drift velocity is infinite. But let's just stick with this classical picture. Drift velocity is infinite. You see, if you remember our first discussion of what is the resistivity, how do we create these currents, we said that, okay, let's just assume first of all, these parallel plate capacitor, we attach it to a battery. And nobody asked why I draw these shapes like this, but let's just continue. And now we said, okay, so if we put some conductor over here, well, the left-hand side will be positively charged, the right-hand side will be negatively charged. So there will be an electric field created, but the electric field, electrons will just move in this direction. And the electrons will be picked up by this positive charge and just to the battery. It will be sent to the battery. So how does this work? Well, basically the battery, as one of your friends had pointed out, it just takes electrons from its positive terminal and gives away electrons from the negative terminal. And now we say that, okay, they accumulate over here, creating this charge, this current inside, and as the charges are moving from one side to the other side, it's just picking up the charges from one end of our conductor and putting it on the other end. Now let's just imagine that these charges in my conductor can move infinitely fast. So whenever there's one positive charge over here, one negative charge over here, that negative charge will instantly move to the other side. So there will be no accumulation of charges on these plates, on these connections. So there won't be any electric field build up over there. Now let's imagine two of them. Let's say that VD is, on the lower one, is almost infinite. The other one it can have some value. Let's assume we close the switch. We close the switch, so there will be some electrons moving around. Well, the electrons that come over here, they will instantly move to the other side. So they will be just running through this resistance. So there will be no accumulation of charges over here, but since there are no accumulation of charges over there, the electrons will be just pushed through this one. And they will just close our circuit. Let's imagine an electron that reaches the top part. There's an electron. The drift velocity here is not infinite, so it has a resistance, so they will start accumulating over here. But here you have a conductor, a connected conductor. One end is negatively charged, the other end will be neutral. But that means there will be an electric field between these two. So the electrons will just from here, they will move back here. But once they reach here, they will be just transferred to the other side. So they will not be staying here long enough to be transferred to the other side. And since they will not be there long enough to be transferred to the other side, no electrons will cross this conductor. All of them will cross this one. This is what we call a short circuit. Let me ask one more question.
I understood this example, but I don't understand the rules.
Which one? This one?
Yeah.
Basically the same idea. You see, here we have a resistanceless conductor. So whatever electron comes over here, it is immediately transferred to the other side. There won't be any accumulation of charges over here. But if the charges move to, let's say, over here, there will be some accumulated charge. But if there are accumulated charge, there will be some electric fields created that will cause those electrons to go back to this wire. So there won't be any buildup of electric field in these wires.
That the electrons will return to that.
I mean, even before they can reach over there, also keep in mind that the distances the electrons covered are negligible. They don't really go anywhere. So although we are always saying that, okay, the electrons are moving all the way around, even that doesn't really happen. So the electron doesn't start from here, go all the way up there, then come back. So already, as some of the electrons in these wires are moving up, they build up an electric field that will push them in this wire. Because there's an electric field over here. Now, when we were discussing electrostatics, about this one.
You said that the electrons aren't actually moving from one side to the other. And is that like flowing liquid? Like other electrons pushing other electrons?
Well, it's not the electrons pushing other electrons, it's the electric fields pushing the electrons around.
Yeah, okay. But
And the electric field builds up almost instantaneously.
in the end, it looks like it's flowing.
Sure. You see, if you just take a long hose of fluid, since all the fluid starts moving at the same time, the moment that you open up the water tap, you get the liquid flowing out from the other end of the hose. Because all of them start moving at the same time. Well, in the case of the fluid, it's the fluid molecules pushing each other around. In the case of the current, it's the electric fields pushing all the electrons at the same time. This one. This one. Here. No. Here the current is 0. Here the current is non-zero. Well, you see, one thing that is misleading is treating this problem as if there is a single electron moving around. What is actually happening is all the electrons over here, they will be, let's say, and they will start moving, let's say, for an instant to create a current across this one. They will just start. But the moment they start, they will be creating some electric fields that will be pushing those electrons back through this wire. So even at the moment that they start, before they can even move, they will be pushed back to this conductor, this resistanceless conductor. It will be 0. There won't be any current running in this one.
Just maybe answer this question. It says, you said that I is non-zero. Is it I infinite?
Well, in this case, yes, but let me put a resistor over here. Let me ask one question to you. From electrostatics, we say that in a conductor, we cannot have any charges. Even if there is a cavity in the conductor, unless we put some charge inside the cavity, there won't be any charge on the inner surface. Let's imagine this one. I put a negative charge over here, a positive charge over here. Is this possible? Well, the positive charge and negative charge, they will be just attracting each other. So they will not be just going around to the other side to neutralize each other. So, is this possible?
There's still resistance in the cavity with the ions that they take out from the conductor and then they neutralize it.
Do you agree with him? Do you understood what he said? You see, he just said that, okay, we can imagine this as a circuit. If this is as a circuit, here we have an infinite resistance across this one. And here we have zero resistance since it's a good conductor. Here there is zero resistance. Well, even if it's not a good conductor, a finite resistance, not an infinite one. So there will be a current running through like this. That's what he claims. Right? Let's say 10 to the power minus 5 millimeters. Is that small enough? How can we prove it that it cannot? Remember, we have Maxwell's equations. We can use all of them. Let's assume that it is possible. Then there will be some electric field lines in the cavity, right? So let's say one of those electric field lines will be this one. Let's imagine, and let's not imagine, we have the Faraday's law. There is no time dependence over here. Nothing is dependent on time. It's electrostatics. So this should be equal to 0. For any closed loop that you can imagine. Let me imagine such a closed loop. In this segment, the electric field is 0. In this blue segment, the electric field is non-zero. It's in the same direction as dl. So basically, if E is not equal to 0 in the cavity, this E dot dl will be equal to the integral of E dot dl in the cavity plus E dot dl in the conductor. Well, in the conductor, the electric field is 0 always in the electrostatics. So this is 0. So since the electric field is not 0, this is non-zero, but this should be equal to 0. So we reach a contradiction if we assume that E is non-zero in the cavity. So that is why even such a configuration of charges is not possible. Okay, so that's basically all I will be discussing. Yes, your questions.
It's quite obvious that, in the sense that plus charge has electrons near, the attract electrons near each other.
But this negative charge is also close to that electrons, and it will be pushing them away.
Not as near as the plus.
Well, I mean, if it was obvious for you, that's fine. It was not obvious for me.
So that's not what I mean. How we think of it that way? Isn't that what?
Well, basically, you're right. I mean, the problem is always thinking in terms of single electrons. When we are talking about the conductors, we have many of them. So it's the same problem over here. As you said, there are many electrons. It's not just this positive charge and this negative charge. They are attracting each other. But there are also all kinds of other electrons around. So here it just means that there is a deficit of electrons. There are all the electrons nearby, so they will just fill that deficit. And here there is a negative charge. There are all the electrons nearby, that there's an excess electron over here. So it will be pushing away all the other electrons. So the other electrons will move towards the surface. This deficit here will move to the surface, and on the surface they will basically meet somewhere and they will cancel each other. So it's not that this my negative charge is moving all the way to the other one. So we don't have a single charges over here. I mean, we have many single charges, not just one charge.
Yani burada elektronlar protona doğru hareket ediyor. Protonlar elektrona.
Well, you see, this is a conductor. The nuclei are at rest. The electrons are free to move, so protons cannot move.
Yani bir şekilde bir çekim sonucu birbirini götürüyor.
Well, again, I repeat, it's not the charges move from this minus charge move to the other one and cancel over here. Both these negative and positive charges, they go to the surface. And on the surface, they somehow meet eventually.
Biz bu matematiksel ispatı elektrostatikten
This is true in electrostatics, not in electrodynamics. In electrodynamics, you can have charges inside conductors, you can have electric fields inside conductors, etc. Just batteries, they create electric field inside conductors. Other questions?
How can we create electromagnetic waves with antennas?
Well, that's basically what you do. You just connect them to an RLC circuit.
I mean, what is an antenna?
It's just a conductor in which the charges have accelerated motion. If you just connect a long wire, just take a long wire, connect it to an AC circuit, AC current, or just connect it to the electricity over here, you have an antenna. Take a solenoid, an inductor, connect it to a very large wire, a long wire, and take your RLC circuit, so this is your simple transmitter. So what will happen is you are creating alternate AC current in the circuit, which will be inducing an AC current in your antenna due to these two mutual inductance over there. And so you will be creating a current in the wire. Of course, the top part of the antenna will be positively charged, negatively charged. Charge will be changing, but we don't really care. The important thing is that the charges are accelerating up and down. Since the charges are accelerating up and down, they will start emitting electromagnetic radiation.
Can we charge battery with this configuration?
How do you want to charge it? Take an antenna, couple it to an RLC circuit, and put your battery over here. Well, not like this. You cannot charge it like this because the current will be just moving in opposite directions. So at one instant you will be charging it, at the next instant you will be discharging it, etc. You can rectify that and connect it to a battery, and you can charge it. Now the problem is how long that will it take? You wouldn't like to wait that long. Because the energy, I mean, even here we are subject to electromagnetic radiation of all kinds. I mean, if you just open the radio here, you will receive transmission. That is a kind of electromagnetic radiation. There is some energy coming here, but that energy is very weak. So the radios, they still use some batteries to enhance that signal. That's the cost energy. If you go to a very quiet place, you take a very close to a very strong signal, you can construct a battery without any, you can construct a radio that doesn't use any batteries, just using the energy in the electromagnetic radiation, but the quality will not be that good. There are people who are trying to build, for example, very small sensors, biosensors, that will just trap that electromagnetic radiation, use the energy in the electromagnetic radiation as their energy source. And they don't require any batteries.
In electroscopes, can electric field waves form closed lines?
In electro? No.
Only
Well, you see, if you want to have closed electric field lines, for a closed electric field line, this will be non-zero. And Maxwell's equations tell me that this loop integral is equal to this one. So you cannot have closed electric field lines in statics. You have to have some dynamics over there. Something, the magnetic field should be changing in time. Otherwise, you cannot have closed electric field lines.
Accelerates a charge and creates electromagnetic wave. So in every direction of, for example, I have a charge. And accelerating in which direction? All directions.
Let's look at this one. This is the radiation that we create. This is the expression. So you see, if sine of phi is 0, you don't get any radiation. So if you look at over here, phi is 0 is just, or phi is equal to pi is this line. So if the charge is accelerating in that direction, there is no electromagnetic radiation in that direction, no electromagnetic radiation in that direction. The maximum is in these two directions. If you would just plot the magnitudes as a function of the angle, this is the magnitude. This is r is equal to sine phi. The distance from the origin tells you the magnitude. At phi is equal to 0, and at phi is equal to pi, it's 0. There is no electric field. There is no radiation emitted. The maximum is in the perpendicular direction. Well, this is a common function, sine of phi.
Do electromagnetic waves have dual nature?
What do you mean dual nature? Let's not go into the quantum mechanics, if that is what you mean by dual nature. Let's stick with classical physics. You will be able to ask that question next year.
Next year, ask on.
It feels like if we stop the time, there will be a point that just like we it's like yani sanki bütün zamanda dursak bir ara sanki bir şey yok, bir şey ait edecek bir şey biraz.
Well, moving with respect to what? If there is no time, there is no motion.
create electromagnetic wave, I need charge to move or accelerate.
Accelerate. Just motion is not enough. It has to accelerate.
I have charge instead. I can accelerate it. So am I creating electromagnetic wave?
Well, let's see. You have many charges. Okay, so all of them will be creating some electromagnetic radiation, and the radiation they create will all be proportional to the Q, their charge. So if you just move them around, just like this, well, they will be basically at the same distance, their acceleration will be the same, all of these terms will be more or less the same, if you want to calculate the total radiation. So the total radiation will be proportional to the total charge of your pen. So what is the total charge of your pen? So you are not creating an electromagnetic radiation. They are canceling each other. If you had a charged object and just move it like this, then you would be creating electromagnetic radiation. Yes, other questions on this course?
Can an alternating source be anything but an LC current circuit? The alternating source circuit.
Okay.
No, it's not here. Yeah. Can it be anything but an LC circuit?
Why can't it be an LC circuit?
Can it be anything else other than an LC circuit?
Well, just look at the dams. I mean, there are no LC circuits over there. They are creating an alternating current.
Dams.
Yeah, the way we generate electricity, most of it. Or the... So you have these rings, like in the simple picture, that are rotating with some given angular frequency. They are not LC circuits, but nevertheless they create AC current.
I'm not sure, but on LC circuits, the current oscillates. And the energy of the capacitor turns into energy of inductor.
True.
But as current oscillates, charges move back and forth, and they create electromagnetic radiation with some energy.
Sure, that which we are ignoring over here.
Does the system eventually stop?
In realistic system, of course, it will stop. Furthermore, there is also the resistance of the wires. Eventually it will stop. But the energy loss in the resistance and the energy loss in, let's say, the radiation, it will be small. I mean, you can arrange such a circuit which will keep oscillating, let's say, hundreds of oscillations before it stops. But of course, eventually it will stop. Well, in fact, one system that is similar to this one, let's see. Let's just take this capacitor. We had already said that it will be, if you apply a time-dependent current to this capacitor, the charge will change, or the electric field will change, so you will be creating an additional electric field inside. Now, so okay, if there is if you are creating a time-dependent electric field, which will create a magnetic field inside, and that magnetic field will create an additional electric field inside. So the electric field will not be just simply sigma over epsilon 0. There will be also this additionally induced electric field if you apply a time-dependent current. Now that electric field, if you remember our expression, the induced electric field increases linearly. If the induced electric field increases linearly as you go away from the center, the total electric field will be zero at somewhere, at some radius from the center. The total electric field will be E0 plus E induced. E0 is constant, but the induced electric field increases with distance from the center. So at some point, at some distance from the center, it will be zero, the total. If the total electric field is zero over here, well, you see, how do we create an electric field? Well, basically what we did was, you just connect it to an AC source, or even, no, AC source is fine, or even an inductor. Okay, so this will keep the charge from moving. This will cause the charge to move back and forth. So it's creating a time-dependent charge, a time-dependent electric field. That time-dependent electric field will induce a magnetic field, which will induce another contribution to the total electric field besides the signal grips from zero, etc. And there will be some distance across which there is the electric field is zero. Now, instead of using all these wires, you see these wires are resistanceless in the ideal case, so there is no electric field in these wires anyway. Instead of using such wires, let's just take our capacitor and connect the top plate with the bottom plate by a conductor. Why not? There's no electric field there. There won't be any additional charges, let's say, except on the ones that are carrying the currents. Well, if you take such a system, you already have your inductor over there. You see, every circuit is kind of an inductor on its own. So you just take this one, two parallel plates, connected. These are all conductors, all surfaces. This is what we call an electromagnetic cavity. The charges will constantly move from the top to the bottom, from the bottom to the top. And you can even build this from a superconductor. And then just build one of these. And then you can build some accelerators. Well, because you have regions where you have a constant electric field will be oscillating back and forth, so you just may synchronize your system such that when the electric field is in one direction, you send your charged particles through it, so they will just accelerate, and then you just make them go around after some time, and just make sure that they just pass through this device exactly at the time when the electric field is back in the same direction. And you can build it from superconductors, so they will be stronger and there won't be any dissipation, etc. And the possibilities are kind of wide. It's just up to your imagination. Well, this is just like how, let's say, in a sense, it's just like how flutes work. These blown instruments, musical instruments. You can, for example, just send some electromagnetic wave through some opening. You just create some opening. If it is at the correct frequency, etc., you can just start these oscillations of PLC circuits. Saying that they will store energy in it, and you can just use it for whatever you want. Or just send some charges. If you just send some charges, you can excite these oscillations of the electromagnetic field inside at a given particular frequency. You don't have to send your charges at a given frequency, but the oscillations that they will excite will be of a given frequency, and then you create an electromagnetic radiation of a given frequency. Anyway, 2 more years. Okay, so let's conclude the lecture at this point. And well, unfortunately, I will not be here in your final exam, so I will not be able to explain the questions to you. But hope to see you next year in the department. Hopefully not in this classroom. Yes.
Tatil mi? Ay ben sınıfı geçeceğim büyük ihtimalle şampanya falan patlatmak istiyorum.